Hi everyone. So this is a question I had posted on LinkedIn, and so I thought I'll discuss the solution for that. And it's a very interesting question. So I wanted to set a problem. This is more of an assignment problem that I designed probably 5 years ago when I was just new to teaching. And at that time, I wanted a question, one single question which can test their analysis skills of most of the single stage amplifier structures. Not only that, also this problem requires to have a decent understanding of frequency response of amplifiers. Okay, so even though the circuit by itself looks pretty complicated, at least for the student who's going to see it in their second or third year undergraduate studies. But if you look at the circuit, there are some circuits which are repeating. So if you look at this circuit here, it's very similar to the circuit shown here. Okay, I've just replaced the positions of R and C, and the input here goes to PMOS, here the input goes to NMOS. In fact, both are just common source amplifiers. They both are very similar circuits. Then if you see this circuit here, this is repeated twice. So we have to understand what is this circuit doing. Okay, and finally, we'll just analyze we'll see what is the transfer function of the amplifier structure shown here. Okay, so there are, if you observe the circuit, X1 is the input, X2, X3, and X4 are internal nodes. So they are going through some transfer function, and I'm just summing up, or I'm just passing it through another circuit. So if you recall from one of my older lectures, this circuit is a voltage averaging circuit. So I'll talk about this as well very briefly. Okay, so once you realize all of that, it's a very simple problem. After that, it's just how accurately you get your results. In fact, it's not even complicated. The frequencies that I have chosen will yield very simple results. So we will use phasor or vector analysis to solve these problems. But before that, we have to understand what is the transfer function of each of the circuits. Okay, so I designed this some 5 years ago, and that I was very new to teaching, and I wanted students to, this was more of an assignment problem, not an exam problem. So it would take a longer time probably when you see it for the first time in an exam. But an assignment problem, students have their own time and they can think and analyze this. So to analyze the circuit, so I'm applying a summation of three sinusoids of three different frequencies. So I can always apply principle of superposition. I can just find out what is the output for each sinusoid, and then I can finally add all the three outputs. Okay, so first we'll analyze the building blocks of this amplifier circuit. So just to quickly state the assumptions, I have given lambda as 0, which means no channel length modulation. So R0 is infinity for all the circuits, and the biasing is not fully shown. So we can assume all the transistors are in saturation region for our analysis purposes. And you don't have to consider any parasitic capacitors for these MOS devices other than the explicit capacitors which are shown in the circuit. Okay, and I've also said that the mobility of PMOS is 1/2 of the mobility of NMOS. So if I size a PMOS device as 2W, then the transconductances will be same for both the NMOS and PMOS. So if I size the NMOS as W, PMOS as 2W, and I can assume that they both have similar transconductances. I have not shown the bias currents here, but that's a reasonable assumption to make. They're, in most of the cases, they are connected in series. Wherever they are, they're connected in series. So I can assume their bias currents to be nearly the same. So with these assumptions, I'll first analyze the first, I'll just reduce the simple circuits. So if you look at this amplifier structure, this circuit here, so this circuit is a voltage subtractor. So I've just drawn it here. So if I feed V1 and V2 at the gate of two NMOS devices shown here, I can apply principle of superposition and solve this. So first I'll assume V2 is 0. If I assume V2 is 0, the voltage at this node is simply V1 itself. It's a source follower, and the looking down impedance is infinity because R0 is infinity. So a source follower, R0 is infinity. So if you increase this node by delta V, source will also increase by delta V because the current cannot change. Current is constant. So the voltage gain is 1. So you get Vn as it is at the output. Now I'll short the gate of the upper NMOS and apply V2 at this node. Now this is a common source amplifier and the load impedance is 1 by GM. Okay, R naught is infinity, so it's otherwise it would have been 1 by GM in parallel with R naught. Since R naught is infinity, it's just 1 by GM. So the gain of this common source amplifier is minus GM RL, and it's minus GM RL is 1 by GM, so the gain is minus 1. So you will get V1 minus V2. So it's a voltage subtractor. So if I have two NMOS amplifiers configured this way, then I simply get a voltage subtraction. Okay, so I'll come to this circuit, but before that I'll analyze a simpler one. So this circuit here is I think most of you might have at least seen a version of the circuit in what we call class AB amplifiers. When you, at least if you have studied some basic audio amplifiers or power amplifier structures, you can quickly recognize the circuit. Small signal wise, again, to simplify the analysis, I can analyze it this way. I can assume that I have applied two identical inputs, Vi, to these two amplifiers. So it's a common drain amplifier, NMOS common drain and PMOS common drain amplifiers connected in parallel. Okay, that's the structure here. So the voltage gain from this point to this node will actually be, you can, assuming the transconductances of both the NMOS and PMOS are the same, okay, assuming this transconductances of NMOS and PMOS are nearly the same, I can simply say that the voltage gain at this point, I'll leave it as an exercise to you. You can easily show it's half. It will be Vi by half. Okay, so your load impedance will be 1 by GM. And so if you connect it with a load impedance of 1 by GM, you can show that it will give you a voltage gain of half. Okay, so if you recall from some of our old lectures, we said that a voltage follower circuit, an NMOS voltage follower, can be drawn by its equivalent Thevenin equivalent. The Thevenin equivalent is Vi as it is, and the Thevenin impedance is 1 by GM. So it behaves like an impedance transformer. So that's what I said. If you look at this node, you can represent a source follower with this voltage and resistor model. And if you connect a load resistance of value 1 by GM, then you get a gain of half. So that's what I was trying to say. Okay, if this node is open circuit, if the load is infinity, then the voltage Vi appears here as it is, you have a gain of 1. So which is what was happening here in the first case. Okay, when we were analyzing the first half of the circuit, so we said the gain is 1, that's because of this. In this case, you have a loading effect and the load is 1 by GM, so therefore the gain will be 1/2. Similarly, you can assume, I've assumed the gain, the input to the PMOS as 0 and showed the gain is off. Similarly, I can assume NMOS's gate is at ground. If I apply Vi here, this is again a source follower, so you'll get a gain of half. So you will get Vi by 2 plus Vi by 2. So the total voltage at this node will be Vi itself. Okay, so that's the voltage at this node. Okay, so that's it. So if you keep this point in mind, it's very easy to analyze. So what I have done here is that, so if I have a structure like this, so I made a small typo is in the circuit. So I said this W is W1 and W1. This should have been 2W1, but it really doesn't matter. W1 is infinity. So when I say W1 is infinity, whatever load impedance you connect here, what it means is that this circuit, the voltage source follower circuit, can be represented by a Thevenin equivalent of value Vi, and the output impedance of this circuit is simply, you're looking into the source node, you're looking into the source node of both the transistors, it will be 1 by GMN in parallel with 1 by GMP, and that is going to be, I'll call it 1 by GMN plus GMP. Okay, that's the output impedance seen at this node. And since I said W1 is infinity, this term 1 by GMN and GMP will be infinity. So therefore 1 by GMN plus, so since W1 I've set that to be infinity, 1 by GMN plus GMP will be 0. So this behaves like an ideal voltage buffer. So it transfers the same voltage with 0 impedance. Okay, so that's the purpose. So if you see the circuit here, you can just blindly replace it with, so this part of the circuit, whenever you see this amplifier here, you can just replace this with a buffer of voltage gain 1. So that's the purpose of the circuit. Okay, so you think for yourself, why did I put a buffer there? So that, I didn't want the gain of this amplifier to be impacted by this RC sections. Okay, so I didn't want them to load it. So that's why I introduced this buffer here. And with similar reasons, I introduced another buffer here. So this circuit here, you can just replace it with a VCVS, voltage control voltage source, with a gain of 1. That's it. Okay, so that's one circuit. Yeah, so now I'll analyze this circuit here a little later. It's again a very simple circuit to analyze it. I'll probably write the expression here itself. It's simple to analyze this circuit here. So let me just erase the rest. Yeah. So this circuit is a source follower. It's a common source amplifier. So you're applying input at the gate of an NMOS, and you're taking the output at the drain of this NMOS. So it's a common source amplifier. So VI here, you have a capacitor. I'm just redrawing the circuit. A capacitor C connected between gate and drain. And if you look at the upper transistor is just a diode connected PMOS load. So this is the load offered by this PMOS device. So even though you have a resistor here, I've said ignore the parasitic capacitors. Since the gate current is 0, there will be no current flowing through the resistor. So I can assume the resistor is a short circuit. It really doesn't matter. So the load offered by this PMOS is just 1 by GM. So I can just replace this PMOS by a resistor of value 1 by GM. So I've sized it such a way. So this is W, this is 2W. So I can assume the load offered by the PMOS is just 1 by GM. Now you have to analyze this circuit. So I said, if you go back to the initial lectures where we analyze common source amplifiers, so first find the DC gain. The DC gain will be -1. So GM of this NMOS, minus of GM into this NMOS into load resistance. So minus GM RL is the DC gain, and that will turn out to be -1. And this circuit has 1 pole and 1 zero. So you can easily find the poles and zeros. So you can use the techniques I've discussed in the previous lectures, how to intuitively find poles and zeros in a MOS amplifier circuit. Okay, so you can easily show the 0 is going to be 1 minus SC upon GM, and the pole will be at GM by C. So the transfer function will be 1 minus S. This will be a right of plane 0. Okay, so I'm not spending time talking about it because I'll refer you to the previous lectures. You can go through the lectures on analysis of common source amplifiers and find these results. They are very probably I've already spent time there. So I'm not spending any time now. So the pole is given by 1 by SC by GM. This is the transfer function of the circuit here. The same transfer function holds even if I make the input as PMOS. So if I choose, for example, which is what is in the last part of the circuit, the last part, if you notice this here, this part of the circuit, the PMOS input is fed to the PMOS gate. So you have the circuit that looks like this. And input VI is applied here and V0 is taken out here. So I can just redraw the circuit in a similar way. So you have, it's a Miller capacitance actually connected between input and output, VI and V0. And similarly, I can just reduce the load to an NMOS and a resistor this way. Okay, and the looking down impedance will be just 1 by GM. So I can replace this guy with an equivalent resistance, AC resistance of 1 by GM. So then the transfer function reduces to the same as we have discussed it for an NMOS input. So it will be minus of 1 minus SC by GM divided by 1 plus SC by GM. Okay, so in this question, I have specifically given GM equals 1 by R. So I'll just use GM equal to 1 by R interchangeably. Okay, so keep that in mind. So I can also write this as 1 minus SRC. Okay, so I've given this assumption in the beginning itself, in the question itself. I've mentioned GMR equals 1. So GM equals 1 by R. This is an assumption. So it just makes the analysis simpler. That's why I've given that. So I can also write it as 1 minus SRC by 1 plus SRC. This is the transfer function of the first two amplifiers, the first amplifier and the last stage amplifier. Okay, so now with this in mind, we will just analyze the one circuit which is left out, which is the upper half of the circuit. I've already said that it's an averaging circuit. So how do you show it's an averaging? So we can apply principle of superposition, assume x2, x3, and x4 are 0, and figure out what is the voltage. Now, before we analyze the circuit, you have to be a little bit careful here. So it's the load here is a RC section. Okay, so let's call this node as V intermediate. So let's or VO1, and VO1 to V0 is a high pass filter. Okay, it's a high pass filter with a characteristic that looks like this. So the pole is at 1 by 100 RC. Okay, 100 RC radians per second. That's the pole. After that, after you cross 1 by 100 RC, you'll have a gain of 0 dB or 1. Okay, the input VO1 will be very close to V0. And at 1 by 100 RC, you can say that V0 will be VO1 by root 2. The magnitude will be root 2, phase will be 45 degrees off. But if you are far away from 1 by 100 RC, okay, for example, let's say at 1 by RC, your gain is, the phase shift will be 0 and gain will be 1. So input will appear as it is at the output. Or even at 100 by RC, the same condition holds, input will appear as it is at the output. Now, will this 10C and 10R have any impact on my circuit? So that's what I need to understand. So if you see this 10C and 10R, if you plot its impedance, it's going to look something like this. At DC, it's a series RC circuit. Capacitive impedance will dominate. So it will be infinity. And after a certain frequency, and that frequency is 1 by 100 RC, it's going to behave like a resistor. Okay. And the value of that resistor will simply be 10R, right? Capacitor is going to act like a short and resistance will be 10R. And at the frequency 100R, it's going to be root 2 into 10R. Okay. So it will be root 2 into 10R. Its impedance, the actual impedance plot will look something like this. So that's the Bode plot. But we will just focus on this itself, the asymptotic plot itself, and say that, okay, at 1 by 100R, I should expect an impedance magnitude of root 2 into 10R. After that, at higher frequencies, when I say higher frequencies, 10 times greater than that, I can assume the impedance is going to be very close to 10R or 10 by GM. So keep this in mind. R equals 1 by GM, that's given in the question. So this impedance will be 10 by GM. So when I apply superposition, I'll assume only X1 is present, X2, X3, and X4 are 0. So these three gates are at ground. And the looking in impedance is going to be, you're going to have 1 by GM in parallel with 1 by GM in parallel with 1 by GM. So since R0 is infinity, I can ignore the lower device. That's not small signal wise, it's not going to offer any impedance. So the load impedance will be 3 GMs coming in parallel. So that will be 1 by 3 GM. So that's what I've shown here. For a common drain amplifier, the load is 1 by 3 GM. And the resistance offered by this is minimum value is always 10R. Okay, or 10 by GM. So now if you see, the impedance offered by this guy is at least 30 times greater than, for all frequencies. For all frequencies, it is at least 30 times greater than this impedance, right? So this impedance is approximately 1 by 3 GM. The other guy, minimum value is 10 by GM. So if you see, the ratio is 30. So this impedance is 30 times larger. So I can, for all practical frequencies, I can ignore this guy because it's going to be 30 times larger. When you put two resistances in parallel, the smaller resistance will always dominate. And when the larger resistance is 30 times larger, the parallel equivalent of the two resistors will very closely be equal to the smaller resistance itself. So therefore, you get it as 1 by 3 GM. Now, I have a load resistance of 1 by 3 GM. You can immediately analyze the circuit. So it's a source follower. You can represent the upper half of the circuit, the source follower circuit, as a voltage source of value X1 and a source impedance of 1 by GM. Now the load impedance is 1 by 3 GM. So you can directly see the transfer function is going to be 1 by 4 times x1. So this is for x1. Similarly, you can analyze it for x2, x3, x4. You'll get the same transfer function. So the total output, I'll call it V01, is the average of the 4 inputs, x1 plus x2 plus x3 plus x4 by 4. Okay, it's the average of the 4 inputs. So that's the upper half of the circuit. Lower half, we have analyzed most of the building blocks of the circuit, we have analyzed it. So now all you need to do is find out what is x2, x3, x4 in terms of x1. So this is the lower half of the circuit, x2 and x1. So first I'll go to analyze this part, x2 and x1. I've already written the transfer function for this circuit. So which is 1 minus SC with a minus sign, minus of 1 minus SC by GM by 1 plus SC by GM into x1 of s. So the transfer function is minus of 1 minus SC by GM by 1 plus SC by GM. That's the transfer function. Now if I plot this, now look at this transfer function. So if you recall, this is a simple all pass filter, right? The magnitude of this function is going to be root of 1 plus omega c by gm the whole square divided by the same value omega c by gm the whole square, and you'd get 1. The magnitude is always 1. It's only the phase that's going to change. Okay, so we'll come to the magnitude and phase plots, but before that we'll just analyze the other circuit as well. So here I told you in the beginning itself that you can replace this combination of NMOS and PMOS by a voltage buffer of gain 1. So I can assume x2 appears as it is at these two nodes. So this node is x2, this is also x2. x2 appears as it is at this point. Okay, so that's what I've shown here, x2 here, and what will be the output x3 at this point. Again, I can replace this guy by a voltage buffer whose gain is just 1. So I get x3 at this point. Okay, so the transfer function you can just easily derive, and if you recall, this circuit is just a voltage subtractor. So whatever voltage you get here, so let's call this V1, this is V2, the output here is going to be V1 minus V2, or x3 will be V1 minus V2. So all I need to do is find out V1 and V2 in terms of x2. So that will simply be, this is a low pass and this is a high pass transfer function. So this is, I'm going to call this as V1 of s as x2 by 1 plus SRC, and V2 of s is x2 into SRC by 1 plus SRC. So that's the high pass transfer function. You subtract the two, you end up getting x3 by x2. That's the transfer function of this whole circuit, is simply 1 minus SC by GM by 1 plus SC by GM. Okay, or 1 minus SRC by 1 plus SRC. I've already said R equals 1 by GM, so you get this. If you see this, it's the exact same transfer function of the first stage. The only difference is there is no minus sign here. Okay, it is also an all pass filter with a slightly different phase characteristics. Okay, so now we will plot the phase characteristics. Let's plot the characteristic of the first amplifier. So remember I said I've written it as 1 minus SRC by 1 plus SRC. Since R is 1 by GM, I'm just replacing GM with 1 by R. So I want to plot the response of this filter. Magnitude, since mod of this is always going to be 1 for all frequencies, it's a 0 dB or 1 for all frequencies. The phase is a very interesting profile. So to draw the phase, I said the DC phase is, there is a minus sign, so I'm going to assume minus 180 degrees is the DC phase. Now whenever you're given a transfer function like this, start identifying poles and zeros. And here luckily the pole is at 1 by RC, 0 is also at 1 by RC, but there of course, one is a right of plane, other one is a left of plane pole. So plot at 1 by 10 RC, there will be no impact of zeros and poles, right? So the phase will still be minus 180. From there onwards, once you encounter the pole or a zero, the phase will start increasing or decreasing. So since it's a left of plane pole and a right of plane zero, the phase will decrease for both at the rate of minus 45 degrees per decade. Since you have a pole and a zero, so the slope here is going to be minus 90 degrees per decade. So in one decade, the phase shift will be minus 80, minus 90, so it will be minus 270. So at 1 by RC, so 1 minus SRC by 1 plus SRC, the total phase shift this guy will cause is minus 90 at 1 by RC. Okay, so you can see, if you recall from your basic discussions on frequency response, if you take a single pole system with 1 by 1 plus SRC, the phase shift at 1 by RC is 45 degrees. Okay, so using that, you can say this guy will cause minus 45 degrees and this guy will cause minus 45 degrees. So when you add the two phases, you get minus 90 degrees. Minus 180, you should add it to the initial phase. So you get a total phase of minus 270 at 1 by RC. At 10 by RC, the phase shift will be an additional 90. So 270 plus 90 will be 360. So for any frequency greater than 10 by RC, you can assume the phase shift is 0 degrees or minus 360. So if you apply an input phasor, so let's assume I'm drawing a phasor diagram, phase is 0, it will be shifted by 360 degrees at any frequency greater than 10 by RC. At frequencies less than 1 by 10 RC, that's DC frequencies or low frequencies, it's going to be a phase shift of just minus 1. The DC shift will be just minus 1. Okay, so keep these points in mind. We'll use this to analyze our circuit. The second transfer function, which is the intermediate circuit, that transfer function is just 1 minus SRC by 1 plus SRC. Okay, just to quickly refresh your memory. So this is the circuit I'm talking about. The transfer function of this is 1 minus SRC by 1 plus SRC. So that's what I'm trying to plot here. Magnitude is 1, so I'm not showing the magnitude. Phase, on the other hand, the DC phase is 0, right? So the input is equal to the output, so DC phase is 0. And at 1 by 10 RC onwards, the phase will start degrading, and they will degrade with a slope of minus 90 degrees per decade. Okay, so when you reach 1 by RC, the phase shift introduced by this term will be minus 90 degrees. So minus 45 from numerator, minus 45 from denominator. So the phases add up, so you get minus 90 degrees. And for frequencies greater than, at frequency equal to 10 by RC, it will become minus 180 degrees. The phase shift will be, you can see that at very high frequencies, you can write it as minus SRC by SRC. I can ignore the one term here at high frequencies. So this becomes minus 1 at very high frequencies. So therefore, the phase shift will be minus 180 degrees. So 0, you get phase shift of minus 180 for frequencies greater than 10 by RC. Okay, so that's it. So these are the two transfer functions we have. And once you know to analyze this, it's very simple to analyze the circuit. So now I'll analyze the circuit keeping all these facts in mind. So this circuit, at this point, it's an averaging circuit. So at this point, it is simply x1 plus x2 plus x3 plus x4 by 4. So all I need to do is try to find out x2, x3, x4 in terms of x1 and just add them up. So I can just use phasor analysis to do addition. So it's easier to visualize it in the complex plane. So there are three frequencies here. F0. F0 is given as 1 by RC. The second frequency is F0 by 100. The second sinusoid is F0 by 100, which is 1 by 100 RC. Third frequency is 100 by RC. So these are the three frequencies that's given in the circuit. Okay. So now our job is to analyze. So I've given F0 as 1 by RC here. So there are three frequencies, and we are supposed to find out what will be the response for all these three. So I'll first start with 1 by 100 RC. Now we have seen all our transfer functions. These are the three transfer functions. Mainly we looked at a transfer function that looks like this: 1 minus SRC by 1 plus SRC. Okay. For this transfer function, 100 by, I said 1 by 100 RC is what I'm going to look at, will look like DC, right? 1 by RC is the pole and zero location, and anything less than 1 by 10 RC is going to look like DC. So keeping this in mind, I know that I'm analyzing at DC frequency. We'll see what is the output. So first, let's start with the first circuit. The first circuit transfer function, I'm going to write it here itself so that it's simpler for you to visualize. It is minus 1 minus SRC by 1 plus SRC. So the DC phase shift is 180 degrees. So X2 is simply minus X1. Okay, X2 is simply minus X1 because the DC at DC it's a negative phase shifter. Now this circuit, the transfer function, there is no negative sign. It's just 1 minus SRC by 1 plus SRC. So therefore at DC that gain is as just 1, so X3 equal to X2. Okay, and finally X4 to X3 is same as the first circuit, so that will be X4 will be minus X3. So I can easily see that X1 and X2 are out of phase. So when you add X1 and X2, you are going to get X1, the averaging circuit's output will be X1 plus X2 plus X3 plus X4. X1 plus X2 is 0, right? Since X2 is minus X1. And X3 plus X4 is again 0 because X3 is minus X4. Okay, the final circuit tells me this. So therefore, the output will be 0 for this frequency. When you apply a frequency of 1 by 100 RC, I should expect a 0 output. So this term will not appear at the output. Okay, it's like DC, doesn't matter. Similarly, I'll analyze it for the second frequency, which will be 100 times F0, 100 times 100 by RC, sorry. F0 is 1 by RC, so the frequency here is 100 by RC. Okay, there may be some 2 pi factors, but I'm just trying to come at the idea here. So it's 100 by RC is the other frequency of interest. Now if I look at 100 by RC as my frequency of interest, then since it is 100 by RC will be like infinite frequency. So here you have the transfer functions 1 minus SRC by 1 plus SRC, right? So this is like an infinite frequency. It's greater than 10 by RC. So anything greater than 10 by RC for this circuit can be treated as an infinite frequency. So I'll treat it as an infinite frequency. So using that, I can just analyze the circuit in a much simpler way. The first circuit, the transfer function is minus of 1 minus SRC by 1 plus SRC. At infinite frequencies, the phase shift is 360 degrees, right? If you recall the transfer function, we said that this transfer function, the numerator will give you minus 90, denominator will give you minus 90. So minus 90 is minus 180, and add another minus 180 to this. So X2 will be equal to X1. Okay. Now let's talk about X3 and X2. X3 and X2. X3 here, the transfer function is just, there is no minus sign here. For X3 to X2, the transfer function is just 1 minus SRC by 1 plus SRC. At infinite frequencies, the phase shift is minus 1. If you recall, a few moments ago, we said 1 minus SRC by 1 plus SRC. At infinite frequencies, the numerator will cause a phase shift of minus 90. Denominator will cause a phase shift. It's a single pole system, so minus 90. And numerator is a 0. Maximum right of plane 0, so maximum for phase shift is minus 90. Total phase shift is minus 180 degrees. So X3 will be minus X2. So X1 is X2, X3 is minus X2, and X4 is again equal to X3 for the similar reasons. It's the first amplifier. The transfer function is minus of 1 by SRC by 1 plus SRC. X3 will be equal to X4. So using this, I can write it as X1 plus X2 plus X3 plus X4. Remember, X4 and X3 are the same, so I can write it as 2X3. And X1 and X2 are the same, so I can write it as 2X1, 2X2. Okay, but I know that X2 equals minus X3, so therefore even this 2 will cancel out. So at infinite frequencies, it's cancelling out. At DC frequencies, it's cancelling out. So you will get this term will also not be present at the output. So now we have eliminated both these terms. Both these terms will not be present at the output. Okay. So now we have to, the only term we are left with, the only frequency we are interested in is this one. So if I guess the output for this guy, then the problem is solved. Okay. So to guess that output, so here is where you will see the importance of phasors. I have not used phasor analysis because you simply get X through, you were only getting either in phase or out of phase. So now we will see the advantage of using phasors. So first I'll draw it here. The first amplifier, X2 and X1. The transfer function is 1 minus SRC by 1 plus SRC with a minus sign. Now your frequency is exactly matching 1 by RC. It's matching 1 by RC. Because it's matching 1 by RC, the numerator faces 45 degrees, minus 45, and this will cause a minus 45 phase. So total phase shift will be minus 270 degrees. So if I, on a phasor diagram, I'm going to assume this is 0. So I'll show it as a vector with a magnitude of say 1. Assume x1's magnitude is A. This will be shifted by 270 degrees, minus 270. So I'm going to rotate it here. So this is your input. X2 will be A, but it's shifted by 270 degrees. Now it goes through the next circuit. So if you recall, these are all just all-pass filters. These are all just all-pass filters with a finite phase. There is only phase shifts. And towards the end, I'll tell you what is the motivation behind the circuit. How did I think of the circuit? I'll just tell you guys. I'll just tell that to you guys. But yeah, so this is X2. So there is a 270 degree phase shift. Amplitude is the same. X3, X2 to X3. X3, if you see, there is no minus sign. It's just 1 minus SRC by 1 plus SRC. So the phase shift at 1 by RC from X3 to X2 is just minus 90 degrees. So it will further shift this. I'll use a different color. It will further shift this by minus 90 degrees. So all you have is X1 and X3 exactly in phase. Both X1 and X3 are in phase. Okay, both of them are in phase. Now X4, if you see, X4, it's the same transfer function as the first circuit. So X4 to X3, the phase shift is minus 270. So you'll again rotate X3 here. So X4 will come here. So X2 and X4 will be adding up. So this is the output due to all the 4 phasors. So now you have the phasor, because X1 and X3 add in phase, I will say the total phasor amplitude is 2A. The vector's amplitude is 2A. Similarly, this guy will also be 2A. So the resultant vector will be in this plane. So this will be the resultant vector. And the resultant vector's magnitude is going to be root 2 into 2A. Right? It's just a vector addition. So you can directly show it will be simply root 2. It's just like diagonal of the two. It's like a diagonal of a square. So it will be root 2 times 2A. And the phase shift will be minus 45 degrees. So I can write, I'm feeding an input of frequency A cos, okay, omega naught t, where omega naught is, 1 by RC. The output is going to be 2 root 2A cos of omega naught t plus pi by 4, or 45 degrees. This will be the output V01, right? Sorry, this is the sum of the 4. The output is going to be x1 plus x2 plus x3 plus x4 upon 4. So I have to divide this by 4. So when I divide this by 4, I'm going to get A by root 2 into cos of omega naught t plus pi by 4. Mind you, you're still at V01. So this is the point where we are at in the circuit. This is V01. V0 is just a high-pass filter, and the high-pass filter pole is at 1 by 100 RC, right? And this frequency is at 1 by RC, so the gain is 1. So V0 is also exactly equal to this. It's in same phase. Since it's a high-pass filter, you get this. So the output is going to be A by root 2 into cos of omega naught t plus pi by 4. This is your final output. So the first 2 frequencies don't appear here in the circuit. If you carefully observe this, what have I done? I have just added 4 terms, x1 plus x2 plus x3 plus x4 divided by 4. If you carefully observe, all I have done, the magnitudes of all these terms are the same. But all these x1, x2, x3, x4, they're all just phase shifted versions of x1. Okay, so they're all just phase shifted versions. So this very closely resembles an FIR filter. So that was my motivation. So I thought of, some of you had messaged me, they were asking me for a textbook where I could refer this, where they can refer this question, but it's not from any textbook. I just designed it for a semester, just designed it for an assignment. So this just is an FIR filter. So I just have x1, I'll probably write it in time domain. So x1, and I have x1 of say t minus tau 1, and x minus x1 into t minus tau 2 plus x1 into t minus tau 3. So this is just 4 delays by 4. So if you write the impulse response, you will easily see it's just a finite FIR filter with 4 taps, okay, with some appropriate coefficients. So that was the motivation. So if you give this different frequencies, it turns out that this filter has zeros at certain frequencies where we applied those frequencies, and it delays and does some amplitude scaling, and finally you get the output. So only out of the 3 frequencies, which is 100 by RC, 1 by 100 RC, and finally we applied 1 by RC, only this frequency comes at the output. And the output is A by root 2 times cosine omega naught t plus pi by 4. Okay, so the plus pi by 4 is just to say that it's in the third quadrant. So if you guys recall, the output was in the third quadrant. So that plus pi by 4 indicates that. Okay, if it's minus, I've used this notation, minus pi by 4, the rotation goes this way clockwise. Plus to indicate this signal here. Okay, or I can write minus of 3 pi by 2 plus pi by 4. So that's also fine, but this works. So that's it. So hope you had a great time solving this. Thank you.